Okay, welcome everyone to our, blending out. Welcome everyone to our lecture for tonight. This is our first, I'll switch to speaker view. This is our first event of this sort, so please be patient with us as we try and work out all the technical issues, like my face constantly blending out of the surface of the moon. I'm Dr. Cameron Hummels, a scientist at Caltech who helps organize these events. And welcome to our first virtual lecture. If you're new to these events, which I think we all are, this event will basically have 30 minutes of a public lecture given by our own Dr. Jason Wang, an expert on exoplanet direct imaging. And then following that, we'll have a Q&A session. I'm really blending out. A Q&A session for about 90 minutes consisting of questions from you guys via the YouTube interface, but we also have some questions that we've gotten from our audience over YouTube and Twitter and Facebook over the last 24 hours. And we'll try and address those questions from our illustrious panel of scientists. So we're going to see how this goes and hopefully do more of these moving forward, potentially having one on the low density gas surrounding the galaxy called the circumgalactic medium, given by PhD candidate proto-doctor Yu-Guang Chen, either next Friday or the week after. And then we'll try and have an astronomy on tap in, I think our next one is scheduled for April 20th, 420. So that would probably be two informal 15-minute talks about science, while the speakers and hopefully you can also enjoy a drink. And that will probably, that's usually on a Monday. So anyway, without further ado, I will introduce our speaker. So our speaker tonight is Dr. Jason Wang. He is I had an intro all written out here. He is a 51 Pegasi B postdoctoral researcher in the astronomy department, and he works on directly imaging exoplanets using some of the largest telescopes in the world. So I will turn it over to Jason.
Thank you. All right, so I'm gonna open up my slideshow. How's that look?
It looks great, Jason.
All right, awesome. Well, thank you everyone for joining. Hoping everyone is having a nice Friday evening wherever they are. So tonight I'll be talking to you guys about how we take real images of exoplanets, planets orbiting other stars. None of that artist conception stuff. All right, so if you've seen images of planets in our own solar system, you might have seen some really nice images, such as this image of Jupiter taken by the Hubble Space Telescope. Hubble Space Telescope is in space orbiting Earth, and it took this picture of Jupiter. You can see it's quite exquisite detail. You can see all the clouds, the great red spot of Jupiter. And this is because, the planets in our solar system are relatively close to us compared to other astronomical bodies. We can really study them in great detail. What's more is that we can actually send spacecraft to the planets in our solar system. So this is an image of Jupiter taken by the Cassini spacecraft. So here, Jupiter's in the background. It's way bigger than this image. And in the foreground, you can see Io, one of Jupiter's moons. So Io is about the same size as our own moon. So that kind of gives you a sense of scale, the sense of how big Jupiter is compared to its moon Io. So we can get these exquisite images because we actually send spacecraft to all of the planets in our own solar system. This one was taken by the Cassini spacecraft. It was designed to hit Jupiter on the way there just because it could. So thanks to the relative proximity of the planets in our own solar system, we can actually take these exquisite images of planets in our own solar system and study them in great detail. So here are images of all 8 planets in our own solar system, sorry, Pluto. These are all taken by spacecraft that we've sent to study these planets, including Earth. So these are planets in our own solar system. You might have heard about exoplanets, planets orbiting other stars. They've been quite popular recently in the news. There's been lots of exciting discoveries. Usually, when these press releases come out, they get accompanied with some kind of artist conception like this. So this is for Kepler-69c. It's a planet slightly bigger than Earth. It orbits a star similar to our own sun. But it orbits a bit closer than Earth. It orbits more at the separation of Venus rather than Earth. So this is maybe a Venus analog. But we've never taken actually a picture of it. We don't know exactly how it looks. What we do know is a few fundamental properties about this planet. And what we can do is use that plus our own imagination to come up with one possibility for what this planet could look like. And that's what we see here. But there's many possibilities. We just don't know which one because we're not seeing these planets directly. And that's because most exoplanets have been discovered. We've discovered over 4,000 so far. More than 4,000 confirmed exoplanets. Most of these planets have been detected indirectly through two methods. One of them is the transiting method. So in this method, the planet happens to be at the right orientation so that it actually passes in front of the star from our perspective. And it does this periodically. So as we're monitoring the brightness of the star over time, we see these dips. And these dips of light is due to the fact that the planet is passing in front of the star, blocking out part of the star and causing the star's brightness to dip. And this has been the most prolific way that we've been able to detect exoplanets so far. But in this way, we're only indirectly inferring the existence of the planet. Similarly, a second technique is called radial velocity. And in this technique, we utilize Newton's third law of motion, that every action, there's an equal and opposite reaction. So as the planet is orbiting and getting tugged on by the star, and the star is actually being tugged on by the planet. And this tug doesn't disturb the star too much because the star is so much more massive, but it causes the star to wobble. And when the star wobbles towards us, Doppler shifting causes the star to look bluer. And when the star wobbles away from us, this Doppler shifting causes the star to look redder. And this periodic reddening and bluing of the star is how we can infer that there's a planet around the star. But again, in both this method, the radial velocity method, and the previous method, the transit method, we're studying the star, and through precise measurements of the star, we're inferring the existence of a planet in the system. Was not to say that these methods aren't effective. These methods have found thousands of exoplanets, but you might wonder, can we just take a picture? A picture's worth 1,000 words. If we can take a picture, we can see the planet directly, maybe learn a bit about the planet. Well, it turns out this is just hard. So taking direct imaging of exoplanets, so taking a picture of an exoplanet, it's like trying to watch a firefly circle a streetlight if you're standing several miles away. So, and this is the best case scenario. These are the brightest planets that we know of in the galaxy. These are planets more massive than Jupiter, very massive, and they're also hot. These are planets that are young. They just recently formed. They're actually letting off heat from their formation. And these planets are trying to see these planets is akin to trying to watch a firefly circle the streetlight. The streetlight, or in case the star, is so bright that it's nearly impossible to see this flicker of firefly circle around it if you're standing, several miles away, not if you were just like right up near to a lamppost. However, we've been able to do this. So here's an image, real image. This is real data of exoplanets. This is the HR 8799 system. So the star is called HR 8799, and the planets, we are not very creative sometimes. We designate them with lowercase letters. So the star is capital A, and the planets are lowercase letters starting with B. So the outermost planet is HR 8799b, is to the top left at around 10 o'clock. And then going inwards, there's HR 8799c, HR 8799d, and E. So these are the 4 planets that we've directly imaged in this system. they might look like spheres, but they're actually single points of light. We're not resolving the surfaces of any of these planets. These are single points of light. We've only spread out that single point of light over a few pixels just because it makes imaging a bit easier for image processing reasons. But we're not resolving the surfaces. These are just single points of light from each planet. But we are indeed seeing light from each of these planets directly. The star HR 8799A is in the middle of this image, is actually blocked out by an occulting disk. So that's where the star is. The rest of the stuff, the glare, the halo that you see, that's actually residual scattered starlight. So that's not like something that's real in the system. That's just the glare of the star that we're trying to remove, but we've done it imperfectly in our data analysis. Just to give you an appreciation, we've removed about 100,000 times the light that you see here. This is just the residual little bit of light that leaks through in our data processing. So I'll come back to the system in a bit more to talk a little bit about it in detail. But first, I like to talk about how we managed to make this image. So how do we take a picture of an exoplanet? So I drew this little cartoon for how we take pictures of exoplanets. So our goal is to image these planets. These are all gas giant planets. They are Jupiter-like planets around their bright host stars. We have to do this from the ground because we need very large telescopes, and we just don't have large enough telescopes in space. But when we do it from the ground, atmospheric turbulence gets in the way. If you ever sat on an airplane and the pilot tells you to put on fasten your seatbelts and get the plane to rumble, that rumbling also distorts waves of light and makes it hard for us to see. It basically blurs the image, makes it hard for us to tell what this faint planet from the bright light of the star. So what we do is we use this technique called adaptive optics. It's essentially akin to giving our telescope glasses. It corrects for the atmospheric turbulence and does this in real time. It has to do this every millisecond. It corrects for atmospheric turbulence. These are very fast correcting glasses. These are not going to your optometrist once per year kind of glasses. They're going to your optometrist once per millisecond kind of glasses. So after we have these glasses, we still need to block out the bright glare of the star. Like I said, the star is very bright. It's generally about 100,000 times brighter than any planet that we know. We use a very sophisticated optical system, which I've here depicted as a thumb. I'll talk a little bit more about about this thumb, but we call it a coronagraph, and this coronagraph blocks out the starlight. And combined with this adaptive optics correction for the atmospheric turbulence, we're able to take pictures directly of the planet. All right, so let's talk a little bit about these two components, the adaptive optics system and the coronagraph. So atmospheric turbulence is quite a nuisance for us. It's great because air is good for breathing and living and us existing as humans, but it really gets in the way for us to taking images of exoplanets. Here's an image of a star that we've taken without adaptive optics. These images are taken about 1 second apart from each other, so you're seeing like quick snapshots of the star. And this star looks like a fuzzy cloud. This is like if you wear glasses like me and you took off your glasses and you're trying to look at some light. It's just like some fuzzy cloud out there. You're not sure what it is, but it's something bright. Now, once we turn on adaptive optics, put on these glasses for the telescopes, that's what it looks like. So that star, which was a fuzzy cloud, now is a nice, clear, crisp image. In fact, if you look closely on this image on the right, you actually can see a second point of light. It's right there, right at about 9 o'clock to the left of the star. This is a binary star companion. This is a lower mass star that orbits this bright star. This lower mass star is only about 1/10 of the flux of this bright star, and even this flux ratio, even a low mass star gets completely lost in the glare of this bright star without adaptive optics. We had no idea the star was here before we turn on adaptive optics. So this kind of gives you a sense for why it's necessary. And this is just a star that's 10 times fainter than the primary host star. If we were to have an exoplanet about 100,000 times fainter than the bright primary host star, there'll be no hope to see it without adaptive optics. So that's why we need it. But that's just one part of the problem. The second part of the problem is that there's a fundamental limit due to the quantum nature of light. So on the left here, this is an image of a star, assuming perfect adaptive optics. You have like the best optometrists in the world. They corrected all the atmospheric turbulence. This is what the star looks like. All these ripples, all this ripples you see, this is due to the wave-like nature of light. This is light from the star interfering with itself. This is due to quantum mechanics. And these ripples of light are inherently brighter than any planet that orbits the star. So there actually is a planet in this simulated image. You just
Looks like we're having problems with Jason's connection here. Hopefully he'll be back in just a moment. Once again, sorry, technical problems. Presumably Jason's connection has disconnected or he's having bandwidth issues. And it looks like he disconnected. Shoot. Okay.
He should pop back in a minute.
Yeah, I imagine he'll pop back in just a second. Thank you for your patience, online audience.
So Cameron, since we're not actually able to take people out observing like we normally would, we could talk about the fact that Venus and the moon will look very stunning tonight if you go out wherever you are after you listen to our Q&A panel and check out the western sky. It's really pretty. You should go check it out.
Absolutely. One thing that I was going to try and put together, I'm not sure if I'll be able to pull this off, but is show a stellarium view of the sky and what people might be able to look at tonight, just directly following Jason's talk. It looks like Jason has returned.
I somehow lost internet for a second.
Is your connection okay?
Yeah, I think it's okay. I just somehow it just blipped off, and if I just turn my Wi-Fi back on, it works again. So
okay. I will spotlight you, and then are you ready to continue?
Oh, sorry about that. Where did I last end before my internet kicked off? Was it here?
Yes.
Did I talk about the left side about this is just without a chronograph, this is the diffraction that we see?
Yes, okay. So we could see the left side, but we hadn't seen the right side yet.
Okay, surprise. This is what happens when you turn on the chronograph. The chronograph suppresses the glare of the star. And you can see it suppresses this diffraction effect. And with that, we're able to reveal that there's a faint planet next to the star. So this is something, even with perfect adaptive optics, perfect correction, we would not be able to see planets without having to put chronographs in because of the wave-like nature of light and the fact that it interferes with itself. So we need both, right? So you might be used to, say, like, glasses as correcting for blurriness and things like that, but you probably haven't dealt with the quantum nature of light as much. But there's actually one time some of you might have experienced this. If you've ever seen a solar eclipse, then you've seen a chronograph in action. So here's a picture taken during a solar eclipse. So here, during a solar eclipse, the moon blocks out the sun. And this is actually quite a coincidence for us. The moon, even though it's much smaller than the sun in physical size, it's happens to be at the right distance away from us, such that it actually has the same angular size on the sky. It looks to us to be the same size. So it's able to just perfectly block out the sun. And when you do this, we actually get to see Mercury during the day. We typically never see Mercury typically never see Mercury with our naked eyes during the day. This is just because it's usually orbiting so close to the sun that the sun is too bright, and we just lose the faint Mercury in the glare of the star, which happens to be the sun. We generally only can see Mercury during sunset, sunrise, and in very specific configurations. and during solar eclipses. And that's why if you've ever been to an astronaut here at Caltech or looked through a telescope at night, you might have seen Venus, Mars, Jupiter, or Saturn, but typically we never see Mercury. It's because it's usually not in favorable configurations. But during a solar eclipse, it is, because the moon is our chronograph. It blocks out the sun, so lets us see these faint planets that we otherwise wouldn't be able to see. Us astronomers, we decided that we didn't want to wait every few years for a solar eclipse to happen and travel to that specific part of the world. And we wanted it to work for any star in the sky, not just our sun. So we invented this concept called a chronograph. It was first invented to study the solar corona, which you see.
Looks like his connection has gone poorly again. Fortunately, I think I can now show what the sky will look like tonight for those of you who are interested. So let's see if I can share my screen. Maybe I can. Sorry guys for all these issues.
It's our first time. We're working it out.
It's our first time, indeed. Okay. All right. Well, while we're waiting for Jason to return and get his internet connection better, I will show you guys a view of what the sky looks like here from California. Well, not from Los Angeles. This is what we would see if there were no light pollution whatsoever, which there's quite a bit. But this is the view looking up in the sky. The S represents the southern part of the sky, looking up in the sky tonight in about an hour's time. So it's still twilight right now, if you look out of your windows. So there's still some daylight and dusk to be seen, which obscures the stars. But in an hour, that should mostly pass. And in the western part of the sky, you'll see the moon, which is just a few days after new moon. And if you zoom in, you can see that there's just a tiny little crescent of it. Similarly, Venus, which looks a bit like a star in the sky, but if you look at it through a telescope, it'll show you the same sort of behavior that the moon is giving, kind of a crescent, in this case, almost a half of Venus. It has phases just like the moon does. And as I zoom out here, kind of redirect this. The other interesting things to look at in the sky, most people can identify Betelgeuse quite readily. Well, Betelgeuse. Can I identify Orion, the constellation of Orion, the Hunter, quite readily by the 3 stars in the belt of Orion? Betelgeuse, of course, has been in the news a lot in the last 6 months because there was concern that as it was fading, it was imminently going to explode in a supernova. It turns out that it's nearing the end of its life, and sometime in the next 10 to 100,000 years, it will undergo a supernova explosion, but the fading has stopped and it's starting to brighten again. So it looks like that won't actually happen, at least in the next few weeks or maybe a couple of years. But something that is quite interesting if you look at through a telescope is the Orion Nebula.
Oh,
not quite getting here.
I'm back again.
Oh, Jason's back. Okay. I'll pause this little.
My phone Wi-Fi because for some reason my router is being unreliable right now.
Okay. Are you ready to go? Should I bring it back to you?
I'm ready to go again.
Okay.
Let's give it a shot and see how it is.
Do a little recap of where we were.
Yes.
All right, we're gonna recap. I'm giving you lots of suspense and not showing you more real images of exoplanets. It's all part of all part of the act. All part of the act. All right, can I go? Let's go. All right. So where were we before? So I was talking about how we use a combination of adaptive optics to correct for atmospheric turbulence, essentially giving our telescope glasses to give it the right prescription. And we use coronagraphs to block something much smaller than the moon itself to block out light from these stars so that we can see these faint exoplanets next to the glare of these bright host stars. All right, so when we combine both of these techniques, we get images. So here is a gallery of real images of exoplanets. All of this is real data. None of these are artist conceptions. This is all real data that I'm showing here. In all these images, you can see there's a bright host star generally, and I've drawn white arrows indicating where the planets are in all of these images. Sometimes it gets a little tricky. These aren't artist conceptions. This is what us astronomers actually look at. So real data is noisy. Real data has artifacts. So I've drawn some arrows to kind of help guide your eye to figure out this is actual real light from a planet that you're seeing, and which parts are just instrumental noise. All right, so for the rest of this talk, I'll talk about a couple systems in detail in particular, and talk a little bit about what kind of research I do and what kind of science we can learn from these images where we are seeing the planets directly. So the first system I'll talk to you guys about is 51 Arri B. So 51 Arri is the star. It's located in the middle here, indicated by the cross in the center. And 51 Arri B is the first planet discovered in the system. That's why it's called lowercase b. It's in the bottom here at around 6:30 o'clock. So 51 Arri B is a Jovian exoplanet. It's like Jupiter. It's about 2 Jupiter masses, we think. It orbits at about 13 AU, slightly further out than the orbit of Saturn. And 51 Arri was discovered in Chile at the Gemini South telescope. So this is where Gemini South is located. It's located in the middle of Chile, near La Serena. It's a 8-meter telescope, 8 meters in diameter, and it sits at an elevation of about 9,000 feet. So pretty high, pretty respectable. Not the highest telescope in the world, but pretty good for our astronomical purposes. We used an instrument called a Gemini Planet Imager. This is an instrument I've worked on quite a bit as part of my own research. It's a series of 3 blue boxes. These boxes contain all the crucial components for imaging exoplanets. It has an adaptive optics system to correct for atmospheric turbulence. It has a coronagraph to block out the bright glare of the star. And it has a very fancy camera to take color photos of exoplanets, which I'll talk about in a second. And so here's to give you a sense of scale, this is the 8-meter mirror of the Gemini South telescope. There's some people at the bottom there for scales to give you a sense of how big this mirror is. It's also quite heavy. I wouldn't recommend trying to move it. It doesn't really move. Don't believe me, I tried really hard. That's a picture of me trying to move the Gemini mirror. Luckily, there's motors so that astronomers don't go there and have to move this giant telescope by themselves. So GPI is at the back of this telescope. So here in this image, the telescope is pointed upwards towards the sky, and GPI, the 3 blue boxes, is bolted onto the bottom of the telescope, and that's the instrument that we're using to take these images of 51 Arri. So I talked about, mentioned briefly before, 51 GPI has this fancy camera that allows us to take color photos. You probably are used to taking color photos with something like your camera or your phone. Your photos are in the visible usually, and these photos are actually a composite of 3 separate images. So when you take a photo with your camera, say this photo of UC Berkeley, that's where I did my PhD. Your phone is actually taking 3 separate photos, one at a short wavelength, a blue wavelength, one at a medium wavelength, a green wavelength, and one at a longer wavelength, a red wavelength. And it combines these 3 images together to produce a color photo. So if you were to look at something such as the trees or the grass in this image, you can see that it's quite bright in the green image, because we know that, and that tells us that the grass is emitting a lot of green light. And you look at the red image, the grass is kind of bright in that, but not as bright as in the green image. So the grass is still emitting a decent amount of red light, maybe not as much as green light. But if you look in the blue image on the left, you'll see that the grass is very dark in that image. That means that the grass is not emitting very much blue light. So from here, you can tell that the grass is very bright in green, a little bit less bright in red, and not very bright in blue. And when we combine those things together, both the camera and our brains tell us that that's some very natural green color. And that's what allows us to tell, which parts of this image is grass and which part of this image is sidewalk. The sidewalk is gray, the grass is green. Similarly, we can do this for exoplanets, but generally we do this for exoplanets in the infrared. So GPI has a color imager in the back. It images in the near infrared colors, and it does this in 37 wavelength channels rather than just 3 wavelength channels. So here is a color image of color images of 51 Area B. So 51 Area B is denoted where the white arrow is pointing on the left. And so this animation on the left is flipping through all the different wavelengths that we've taken images of 51 Area B at. So you can see that at the very smallest, shortest wavelengths, 51 Area is very faint. You can maybe pick it out if you have a very discerning eye. At these wavelengths, there's a lot of water absorption in the planet's atmosphere. So, and the water in this Jupiter's atmosphere is absorbing the light from the star, not the star, absorbing the light from the planet. So that planet is not getting to us. So we don't see very much light at those wavelengths. And then when the water absorption disappears at around 1.57 microns, and then we're seeing a lot of flux from this planet. We're seeing a lot of heat being irradiated from the planet because it's not being absorbed. But once again, once we go to longer wavelengths, methane absorption starts kicking in. At these wavelengths, that's where methane absorbs at, and there's a lot of methane in this planet's atmosphere. So that methane is absorbing the heat being radiated from this planet and not letting us see it. So from this color image that we took with GPI at the Gemini telescope, we're able to tell that there's definitely water and methane in this exoplanet's atmosphere. This water and methane isn't like the water and methane on Earth, it's like the water and methane in Jupiter, actually. This is one of the, and from this spectrum, we're actually able to say that this is one of the most Jupiter-like exoplanets that we know of to date, because we're able to actually directly see the emission coming from the exoplanet. We can see it at different colors, different wavelengths, and tell what kind of composition makes up the atmosphere of this Jupiter-like planet. But this is just one snapshot in time. So these images were taken basically on the same night, just at different wavelengths. We can also take images over the course of many nights and piece together time lapses of these planets. So here is a time lapse of 51 Area B in orbit around the star. So here the star is denoted helpfully by the yellow star symbol, and 51 Area B is to the bottom left and is orbiting clockwise in the image. This is a time lapse taken with 4 years of data by the Gemini Planet Imager. And using this data, we've been able to study the orbit trajectory of this planet, understand the dynamics and the dynamical history of this planet and how it formed. So that's one exoplanet system. The second one I like to take you to is using telescopes in Hawaii. So here we'll be using the Keck telescopes. They're located on top of Mauna Kea on the Big Island in Hawaii. There's actually 2 Keck telescopes. They're both 10 meters in diameter, or some of the largest telescopes in the world. We'll be using Keck 2, which is the one here to the left in this image. And it's located at 13,600 feet. So it's just very high. This is actually where oxygen, there's actually not much oxygen. So trying to operate telescopes at this high altitude is sometimes a little tricky. So oftentimes we usually operate it remotely from places like Caltech, where we have a lot more oxygen because we're at lower altitudes. With this telescope, the Keck 2 telescope, we were able to take this image of HR 8799 that I showed you before. So here, there's 4 arrows in this image, and they indicate the direction of orbital motion for these planets. So this is one of the first images taken of the 4 planets in the system. But however, over the last 7 years, we've been actually accumulating more and more images. So here's a movie that I made with Christian Marois of the 4 planets orbiting HR 8799. This is kind of the initial frame that you were seeing before. And here is a time lapse of the last 7 years of these planets orbiting. So you can see that the planets are orbiting in a counterclockwise fashion. And if you look closely, you'll see that the innermost planet, HR 8799e, orbits faster than any of the outer planets. For example, if you compare it to HR 8799b, which is the outermost planet, it orbits a lot slower than HR 8799e. This is just a reflection of Kepler's second law that planets closer in move faster. I've worked quite a bit on this system. One of the very interesting and cool things about this system is timescales. So this system was born about 40 million years ago. If 40 million years ago sounds like a long time, but it's actually not too long of a time, even in geological timescales. So the dinosaurs were roaming the earth about 100 million years ago. They went extinct 65 million years ago, and 20 million years after the dinosaurs went extinct, HR 8799 and the planets around it were born. So this is a relatively young system in astronomical timescales. Even in some geological timescales, these planets are younger than dinosaurs. So what's interesting about this is that we can actually make orbital constraints based on this. We know that these planets have lived for the last 40 million years. That means that they've had to reside in an orbital configuration that's stable for the last 40 million years. We can't let, in the last 40 million years, these planets couldn't have tried to kick each other out of the system. And this is actually a very powerful constraint because these planets are very massive. These planets are about somewhere between 5 and 10 Jupiter masses. So if you were to, so here I plotted 2 possible orbital solutions for these 4 planets. I plotted the position of the planets as the circular markers and their orbital trajectories as the lines around them. And I'm rewinding time. I'm still simulating these planets backwards in time. So you can see these planets are orbiting clockwise now, as opposed to counterclockwise in the time lapse, because I'm simulating these planets backwards in time. And what I'm trying to do is trying to understand which of these orbital configurations are actually valid. The valid orbital configurations will have these planets just orbiting very smoothly and interacting very, very little with each other, whereas the orbital solutions that are not reflective reality would cause one of the planets to get ejected and get left out of the system. So here on the right, you can see that this orbital configuration is not reflective reality because this orbital configuration isn't stable, whereas the one on the left will keep going. It'll keep going for 40 million years. So if you are really bored at home, you can watch this as we rewind time for 40 million years up to when the system was born. But we probably don't have time for that right now. So I'll just trust me that the system will this animation will keep going for 40 million years. But basically with this, we're able to infer from these few images that we have, what is the orbital trajectory? What is the orbital trajectory for all 4 planets? And with this, we can try to study their dynamical history. So one of the things that we've learned from doing these dynamical studies is that likely these planets were all formed further out and actually migrated inwards and got locked into the stable orbital configuration. Because this orbital configuration that they're in is so fine-tuned, it's hard to form planets exactly at these right locations, but it's much easier for them to form further out and slowly migrate themselves in and lock themselves into the stable orbital configuration that we see today. So yeah, this is the kind of stuff that we're working on currently and what we can currently study with current technology. You might be wondering, when will we get images like these of exoplanets? When will we get these really nice high resolution images of exoplanets? So like I mentioned before, all these planets we're seeing are single points of light. We're not actually resolving their surfaces. They look like circles just because we're sampling the image in such a way that's good for image processing, but they're essentially single points of light. If we want to resolve the surfaces of exoplanets, we need telescopes about 10 kilometers in diameter. Right now, our largest telescopes in the world are 10 meters in diameter. So we're a factor of 1,000. Our telescopes are 1,000 times smaller than what we need to resolve the surfaces of these planets. It's unlikely that we can build a telescope that big with current technology. However, some people that I've been working with, we've been thinking about possibly using another technique called interferometry to possibly use a bunch of smaller telescopes and use that to achieve the resolution of a larger telescope that we couldn't build fully ourselves. This technique is still pretty nascent. It's nowhere near being able to build 10-kilometer interferometry arrays, but something that's one possible way to resolve the surfaces of these planets. Another thing you might be wondering is, when will we get images of terrestrial planets? So all of these planets that I showed you here today, all the real images that I showed are of planets the same mass or more massive than Jupiter. So these are all gas giant exoplanets. They're not terrestrial planets like Earth. So how can we get images of Earth or Earth-like planets? So that's something that us astronomers are thinking a lot about recently. We have mission concepts for maybe not in the next 5 to 10 years, but maybe in the next 20 to 40 years, how can we build telescopes, particularly in space, that can be sensitive to another Earth-like planet orbiting another sun-like star, if those planets do indeed exist out there. So that's something that we're thinking about. We think we know maybe how to build them, and we're hopeful that hopefully in our lifetimes we'll be able to do such a thing. So that's basically what I wanted to talk to you guys about today. Thanks for your patience and with all the internet issues. Maybe it's everyone trying to tune into this awesome talk. That's why my internet connection is unstable. I'll just leave you here. This is some time lapses of exoplanets in motion that I've made. So these are some of the known exoplanets that we have orbital motion for that you can enjoy. And thank you.
Hooray. Nice work.
Thank you.
All right.
All right.
So,
stop sharing.
We'll go back to our whole panel here. All right. So, thank you very much for that presentation, Jason. Now it's time. Well, I don't know. Should we go straight to the panel, or should I continue to show what's in the sky? I don't know. Maybe that's not much of interest to people right now.
Let's do the panel.
Okay, so we'll start our Q&A panel. First, I want to introduce everyone on the panel. I'll start at the upper left. We have Dr. Ilaria Caiazzo. She's a Burke postdoctoral fellow in the theoretical astrophysics group at Caltech, who works on the last phases of the lives of stars, that is to say, white dwarfs, neutron stars, and black holes.
Hello, everyone.
I'm Dr. Cameron Hummels. I'm a postdoctoral researcher in the department in theoretical astrophysics, and I use supercomputer simulations to understand how galaxies form and evolve over billions of years. Dr. Jessie Christensen is a research scientist at the NASA Exoplanet Science Institute here on the Caltech campus. She discovers, characterizes, and catalogs extrasolar planets, like the ones that she's pointing to in her background. Paolo Madonia is a research assistant in the Observational Cosmology Group at Caltech, working on instrumentation to study the epoch when the first stars and galaxies formed long ago.
Everybody.
You guys just listened to Jason, but I'll give him his spiel as well. Dr. Jason Wang is a 51 Pegasi B postdoctoral researcher in the astronomy department. He works on directly imaging exoplanets using some of the largest telescopes in the world. And finally, but not least, Mia de los Reyes is a PhD student in Caltech astronomy who studies the chemical composition of small galaxies near the Milky Way. Okay.
Hi, everyone.
So welcome to our panel. Let's see, you guys are welcome to ask questions through the YouTube interface. We also have some questions that people have produced for us on Twitter and on Facebook and on YouTube. Let's see. I'm not seeing any immediate questions here.
There's been a lot of questions also during the talk. I just posted them
Oh, you
on
did?
our chat.
Oh, great.
If you want to look
Okay.
at them.
Perfect.
like instruments are able
Oh,
to
yes.
measure a few, that one, yeah. So there's been a lot of people asking questions during Jason's talk. I don't know if we can trace them back to what exactly Jason was talking about, but maybe you can look at them.
I can guess a lot of these, I think.
Go ahead.
All right. Can I just read them off and I'll answer them?
Absolutely.
Okay. So instruments are able to measure a few dozen centimeters per second now, right? So I think this question is talking about radial velocity instruments. So I was talking about how we can measure the wobble of the star, how the star gets bluer and redder and wobbles back and forth, and we can use that to indirectly infer the existence of planets. And yes, it's a very exciting times for these radial velocity instruments. In this year, basically, we're putting online a bunch of instruments that should be able to achieve a few dozen centimeters per second radial velocity precision. And this will allow us to detect lower and lower mass planets. So that's something we're currently working on, is super state of the art. And hopefully we'll have new and exciting results from those instruments soon. The second question, I think, is not there. I think someone else in the panel probably can answer better. Can you imagine if a supernova occurred in the Milky Way right now? The screams from astronomers would be epic.
I think that's referring to the fact that all of our observatories are shut down at the moment because of safety reasons, trying to make sure everybody can stay apart. So if a supernova went off right now, this would be a super bad time. Not that there's ever a great time for a nearby supernova to go by, but we wouldn't be able to look at it.
Yes, that would be unfortunate, but hopefully there'll be other supernovas that will go off that we can study. What are you using as a chronograph, and how do you put it in the right place? I imagine a pin head on a stick, but that can't be right. So that's a great question. I chose not to show what a chronograph is because it's a series of optics, basically. It's not very intuitive. Basically, we do have something kind of like a pinhead on a stick. It's kind of a circular disc. It's really small, and it's what mainly blocks out the starlight. However, that's what usually people see as the chronograph. That's the physical occulter. We call it the occulter. That's kind of like the moon passing in front of the sun, for the solar eclipse. But there's actually a second part to a chronograph. There's actually because we're putting we're putting an occulter in front of the star, that actually creates extra diffraction around the edges of this occulter. So we have to add a second element that blocks this diffraction. There's actually a two optical element thing that composes of a chronograph. The second thing, unless you're an optics person or wants to do some college level physics, I won't go into the details of that, but basically it's two elements that combine together to form this chronograph. One of them is like a little circular disc that blocks out the starlight. Is this IR light reflected from the planet or radiated because this is hot? That's a great question. So that's probably referring to the animation of 51 Ari B I was showing, how we were taking color photos in the infrared. This light that we're seeing is actually light being thermally radiated from the planet. It's not reflected light. This planet is still quite hot. So this planet is actually even younger than HR 8799. This planet is only 20 million years old. So it's actually so young that it's closer in time to us than the dinosaurs. This is quite a young planet. It's about 600, somewhere between 600 and 900 Kelvin. So it's quite hot. So we're seeing all thermal emission from the planet. Does each telescope have its own personality? What do you guys think? Anyone experience some personality with telescopes?
I mean,
Not
for
so
sure, the
much.
different instruments have to be babied in different ways and, be given the right amount of attention at the right time.
I think when you look at the final data, it looks perfect and beautiful, but then you have to know your telescope to really, reduce it in the right way, understand where it fails and what are the problems. So yes, definitely each one has their own personality.
Yeah, Yeah, I was add that like telescopes aren't like cars. Like cars are like mass produced. You know, they're all like all the same make and model, or all operate the same. Telescopes are much more artisanal kind of manufactured things. So like each of them has their own quirks, has their own pros and cons, and they have their own ways of being operated. So for sure, I think every telescope has their own personality. How are you guys able to determine the age of the system? So that's a great question. How can we age date stars? I think that's a whole separate talk in itself. But basically, we're assuming here that the planets are roughly the same age as a star. Based on our current observations and our theories, we think that most of these gas giant planets form within about 1 million years. Which sounds like a long time, but it's really short on astronomical timescales. Usually our uncertainties on the ages of these stars are several million years, so it's well within that uncertainty. Otherwise, we use the stars themselves to age date how old the system is. We use things like the brightness of the star. Younger stars are more magnetically active. We use all of these kind of indicators that all kind of piece together to tell us what kind of age the star is. But it's certainly not an easy thing, and requires people with lots of expertise to figure out what the precise ages of stars are. What sort of mathematical models or tools do you use to reconstruct these orbits? So to do orbital monitoring, orbital monitoring is fairly straightforward. It just follows it follows Newton's laws of gravity. It's just gravity of the star pulling on the planet, and there's actually a nice analytical equation that describes this. But usually the hard part is that we have millions and millions of possible orbits, because we have these small orbital arcs for a lot of our directly imaged planets. They have orbital periods of decades, only seen them for a few years. So we've only traced out a small orbital arc. The rest of the orbital arc could be a lot of different possibilities. So we have to use a lot of statistical inference kind of techniques to kind of guess at what are all the possible families of orbits that could be consistent with the data, and but all could possibly be possibilities for what the future trajectory of these planets could be. What would make them all migrate like that? So this is probably talking about the HR 8799 planets. I was talking about how one of the conclusions we drawn is that these planets have to migrate inwards and lock themselves into this orbital configuration that we see today to be stable. We think that this migration is due to early on in the system's lifetime, when there's a lot of these planets were just born and there's still a circumstellar disk. And what a circumstellar disk is kind of the leftover dust and gas from planet formation. So you form the planets, and then there's all this leftover stuff that's still floating around. And this stuff actually has enough mass, has enough drag that causes planets to migrate. And if they can cause the planets to all migrate inwards and lock them into resonance. So that's what we think is responsible for the migration. And that's actually the last question, I think. What role does gas and dust distributions play? Whoever asked that question completely called it. That was gas and dust are the things that drive the migration of these planetary orbits. All right.
Okay.
So shall we go to the questions that were asked beforehand, and then we go back to the questions that are popping out right now?
Sure. That seems good. I will go. So as Ilaria alluded to, and as I mentioned before, we had a number of questions that people asked in advance over social media in the last 24 hours. And so I'll step through some of those and ask some of our panelists the questions that were asked by social media sources, and then we'll respond to those. But you guys are free to continue asking questions in the YouTube channel, and I'll try and pick out the highlights there, and we'll try and get to that in the next hour or so. Okay, so let's see. Well, since Ilaria started us out, one question that we had on Facebook was, what's the latest update on the search for the God particle and the unifying theory of everything?
Oh, okay. So I guess this is a little bit off topic and it's a little bit outside of my field, but I guess all of the panelists' field as well, because we're all astronomers and astrophysicists. But I can give a short answer to that. So the question was, what's the latest update on the search of the God particle? And so I think what it means is about the Higgs boson. So the Higgs boson, the God particle, is the particle that gives mass to all the other particles, so to all the elementary particles that it interacts with, so electrons, protons, etc. And so you have to think about the Higgs particles like all the other particles. It's part of a field. So the Higgs field pervades the whole universe, and the particle itself is its quantum manifestation. So it's similar to a wave on the surface of the ocean, and the ocean is the Higgs field, right? So that's what people have been searching for a long time, and it's been predicted that this particle existed for a long time, and finally it was discovered in 2012 at the Large Hadron Collider or LHC in Geneva. It was like an amazing discovery, but that wasn't the end of it, because once you discover the particle, it's just half of the way, because you discover the particle, but then you want to really understand how this particle interacts with the other particles, and how this interaction really gives this mass to the other particle. And that's what's going on since then at the LHC. And so it happens like in two ways. So one way is that when this Higgs boson, so when this particle is produced in this collider, it only lasts very, very, very short time. It immediately decays, which means that it transforms into other particles, usually a pair of muons or charm quarks, if you know your standard model elementary particles, but which means like the Higgs boson usually transforms into other particles. And that transformation really can tell us a lot about this fundamental interaction of the Higgs bosons with other particles. And that's what people are working on right now. And the last news I had was in late 2019, there was a conference in high energy physics that says that the ATLAS and the CMS collaborations, which are two big collaborations that work at the LHC, presented a new suite of results which provided new insight into this mechanism. But we are still, again, we're still getting there. We predicted the presence of these Higgs bosons, we discovered the Higgs bosons, and now we are really understanding how the Higgs bosons interacts with the other particles. And then there was this other part of the question, which is like the unifying theory of everything. That's an even harder step, which would probably, as Jason said before, I think this question would probably, would definitely deserve an entire other talk, if not more. But there's been a lot of progress. The idea that a unifying theory exists is not so crazy, because we already unified a lot of theories before, like electromagnetism and weak theory. Like there's all these four forces in the universe, and we're trying to unify this theory of all the forces together. So it's not that crazy, but we are not there yet. And there's been a lot of work in theories around the planet, people really trying hard to get there, but we're not there yet. There's been a lot of updates. If you're very interested, I'm sure we can put together another talk about it, but that's probably beyond my expertise. I'm really giving an update of this.
Oh, that's good. Thank you, Ilaria. Does anyone else want to add anything on that, or are we good? Okay. The next question from Twitter is for Jesse and for Jason. If you were to prioritize 3 exoplanets to visit, which would they be and why? And there's a follow-up question, are exoplanets COVID-19 free?
Sure. So I would like to go to Kepler 452b. So people who aren't familiar with the telephone numbers that we use to describe planets, Kepler 452b is the candidate that we have, which is most like the Earth. So a rocky planet that's in the habitable zone of a star like the sun. It's the closest thing we found to something like the Earth. But I said candidate on purpose because we're not actually sure if it's there. So I'd love to go there so I could just like step out of my spaceship and be like, there it is, it exists, cool, we found it. Or step out of my spaceship and be like, oh, no, we got it wrong, it's not here. So that's the first one. I'd really like to solve that mystery. Is that planet really there? The second one, I'm going to cheat a little bit. It's a system that I'd like to go to. It's called K2138. It's a system of planets found by citizen scientists. And the reason I'd really like to go to it is because the planets in the system are all really close to each other, very, very close. They orbit each other within days, unlike the planets in our solar system, which take months and years and decades to orbit the star. These all orbit, 5 planets orbit within days. So I think it would just be wild to like stand on the surface of one of those planets and look up in the sky and see big, huge planets in the sky. That would be very cool. And then the third one I said that I'd like to go to would be HD 189733b. This is one of the very first hot Jupiter planets that we ever found. One of the reasons I'd like to go there is because it's also one of the most hellish planets that we found. We've been able to study it in great detail. And one of the things we found is that the atmosphere is so hot that it's raining liquid glass sideways all the time. So I just want to go there and see that because that's like, you know, you see these Science Channel, like extreme weather, that's pretty extreme. And the other reason is because HD 189733, as I said, it's really well studied and it just feels like an old friend to me at this point because we've been studying it for 2 decades. And I'd just love to go and see it and be like, I've observed you so many different ways. I'm glad to finally see you with my own eyes. And I'm pretty sure all 3 of those systems are COVID-19 free.
Excellent. And
Let's
Jason?
see. I think the first system I'd like to go to is the system called PDS-70. It hosts 2 newborn planets. These planets we think are still in the process of formation. These are the only 2 planets that we're definitively sure these are planets in the process of formation. So I'd really like to go there and see how these planets are forming and like what exactly goes about into forming planets. That's something that we as scientists are still don't have very much data on, are still trying to figure out how exactly this process happens. The second system I would be interested in going to is Proxima Centauri b. So Proxima Centauri is one of the closest stars to us. It's an M-type star. It's a lower mass red star compared to the sun. And it harbors a potentially terrestrial world around it. And so I like to go and see one of our closest neighbors and say hi to them. And lastly, I'd probably like to go to the Beta Pictoris system. So that's my background that I have here. So Beta Pictoris harbors this massive, what we call debris disk. It's analog to our Kuiper belt, but way more massive. There's a lot more stuff in it. And there's also a 12 Jupiter mass planet inside of this Kuiper belt, and it's stirring up the Kuiper belt like crazy. It's actually stirring up so much that we see exocomets. We see exocomets evaporating into the star all the time. So I want to go there and see this light show of this giant, massive planet stirring up this massive Kuiper belt and causing all these comets to be flying about everywhere. I think that'd be a pretty awesome sight.
Okay, sorry, I'm like phasing in and out here with my background. Okay, if I get close enough, okay, whatever. Maybe I'm just gonna be phased out for a second. The next question is for Mia, and it is, in terms of galactic archaeology, how does the composition of the Milky Way galaxy, our galaxy, compare with galaxies which are relatively close, i.e. like 500 million light years away? Are there any characteristics that are peculiar to the Milky Way?
Yeah, this is a great question, and I love it very much because I am a galactic archaeologist. So like an archaeologist on Earth who tries to study past civilizations by understanding what they left behind, often through stuff like chemical composition. So if you see like a pottery shard and you try to determine what that could be, like what that pottery shard could have been used for, a lot of archaeologists might do things like mass spectrometry or other I actually have no idea what archaeologists do. Maybe they lick it, I don't know. But you can't lick a star. And so when we do galactic archaeology, we have to use other methods to determine the chemical compositions of nearby stars in galaxies. And from understanding the compositions of those stars, we can understand the past events that happen in the galaxies in order to make all of the elements that we see in stars today. So, and as far as, how is the Milky Way different from other galaxies in this, galactic archaeological way? That's a really good question. It's one that I'm not really well equipped to answer, in part because we don't have that many measurements of individual stars in galaxies other than the Milky Way. So for the most part, we're limited to these chemical composition measurements of individual stars in the Milky Way, in some kind of in our nearby neighbor Andromeda, and in the satellites of the Milky Way, and sometimes the satellites of Andromeda. And so there's not a really big sample size to draw from here. There are some pretty big differences between the Milky Way and its satellites. So for instance, the Milky Way is much more massive, and we know that more massive galaxies tend to have more what astronomers call metals, but for everyone else, it's not really metals, it's just heavy elements heavier than helium. Chemists do not like us very much for this reason, because we have this weird terminology. But when we say that Milky Way is pretty metal rich relative to these other small systems, that's been pretty well known for a while. And we know this is probably because the Milky Way has a larger gravitational potential, so it's more able to hold on to heavy elements that are produced throughout its lifetime. Whereas in dwarf galaxies, really energetic events like supernovae can blow a lot of the metals out of the galaxy. And so the stars end up being a lot more metal poor. So that's one major difference. Another major difference is that the Milky Way, compared to its satellite galaxies, tends to have more elements, what we call alpha elements, that are mostly produced in core collapse supernovae. So these are the deaths of massive young stars, supermassive stars, much more massive than our sun. Our sun will not become a core collapse supernova. But the Milky Way satellites tend to have a lot more iron peak elements, which are mostly produced in another kind of supernova called a type 1a supernova. And this is because core collapse supernovae, because these are very young and massive stars that die very quickly, they only happen if you have a sort of continuous rate of stars that are being formed, because you need young stars to die, like very young and massive stars, and they don't live very long. So you need sort of a background level of star formation for them to happen. But in a lot of these dwarf galaxies, the star formation has turned off. And so what we see are the elements that are produced much, much later in other events like these type 1a supernovae. Anyway, I could go on for literal hours about this, but I think we will end it there. Those are sort of two broad differences between the Milky Way and other nearby galaxies.
Okay, thank you, Mia. I had to do away with my moon backdrop, and now you can see my green screen, red screen of a cheap sheet. Anyway, I was phasing out. So the next question we will ask Paolo. It is, can we use simple flattened mirrors for making reflector telescopes instead of using the parabolic ones that people tend to use in telescopes?
I think we would all be really happy if we could use flat mirrors, because they're much, much easier to fabricate and also cheaper too. So we could have a lot more telescopes to use. But actually, the reason we can't use just flat mirrors for telescopes is that they wouldn't be able to bend the light as we want to. Basically, the reason for which we use telescopes is that we want to collect as much light as we can in a single point. We basically want to focus that light in a single point. And this is because the stars and the objects that we are looking at are really faint. Now, to do that, we need to properly bend the light. We need to use curved surfaces, not flat ones, because flat ones can only fold. Well, I can share my screen, Cameron, for a sec. Maybe.
Yes, you should be able to.
Yes, otherwise it's gonna be quite
It's
boring.
the green button at the bottom, in the center of the bottom.
Yeah, you should see that now.
Yes.
Correct? Yeah. So basically what we see, can you see my cursor? as well, or no?
I do see
Yes.
it.
Okay, great. So basically, we see the light from the stars coming from the right in this picture. So we see all these light rays arriving parallel to each other. And if we want them to arrive all in the same point, we need them to reflect over a curved surface. Because otherwise, what happens if, let's play with this little game, which is really useful here. I'm simulating a small beam of light, and you can see these rays are all parallel. Now, if I use a flat mirror, what happens is that I just get another bunch of parallel rays. They're not going to end up all in a single point. Whereas if I use a curved mirror, as you can see, they end up in a single point, which is called the focus. Now, this is like the simplest way to explain why we don't use flat mirrors. And to finish my answer, hopefully, to this question, we don't just use parabolic mirrors. Actually, we use a lot of different curved surface. We use conic, what are called conic surfaces, which can be hyperbolas, parabolas, and so that it's not just that we are fond of parabolic mirrors. We need a curved surface. I hope this answers the question.
Yeah, I think that's good. Can you
Yeah, sure. Stop share.
yeah, stop share. Okay, perfect. Okay, cool. The next question is for me. I'm excited about this. So question, we'll be long gone by then. This is from Biggest Taco on Twitter. We'll be long gone by then, but in 4.5 billion years, will the Andromeda galaxy be distinctly visible when our galaxies, being our Milky Way and Andromeda, collide, or will it just look like slightly more stars? So what this question is alluding to is the fact that our galaxy, the Milky Way, is on a collision course with the Andromeda galaxy, which is another massive nearby galaxy to our own. And eventually they're going to collide and coalesce into a single galaxy that, because astronomers aren't very imaginative, they've named the combination of Andromeda and the Milky Way Milkomeda. So it'll form this massive galaxy called Milkomeda, which I really like. And fortunately for all of us, there is a wonderful, there's a wonderful video of this that shows, there was a wonderful study of this done by Roland van der Merel and Gertina Besla and collaborators about 8 years ago, where they did a computational model of how these two galaxies in the local group would evolve over the next 8 or so billion years. And we can see how these things actually will merge. And we can also see what they look like, what the view looks like from here on Earth. So first I'm going to show you this really cool movie. Hopefully you guys can see this okay. Okay, so this is the Milky Way galaxy from this 8-year-old supercomputing simulation. This is a simulation that's following the evolution of these galaxies. So the Milky Way is in the upper right, and then the Andromeda galaxy, which is our nearest massive neighbor, and also the Triangulum galaxy, which doesn't really play a role in this. It has some gravitational influences, but you can see a clock in the lower right corner showing you time as it passes. And these galaxies are getting closer and closer together. And then woof, they pass next to each other. But you see, galaxies are primarily, even though they consist of hundreds of billions of stars and gas clouds, they're primarily open space, open volume. And so the chances that two individual stars will actually slam into each other are very, very, very small. But the main things that you can see here are, obviously the galaxies lost their disky structure. And when they coalesced into a single object, they look much more kind of like a spherical object. in terms of the distribution of the orbits of their stars, but also everything looks quite red, right? The reason it tends to look red is that blue stars, okay, how far do I want to go back with this? This could turn into like a semester's worth of a class, but I don't want that to happen. When you have a burst of star formation, many stars are produced at the same time. Here, I'll get out of full screen here. Many stars are okay. When you have a burst of star formation, you produce a bunch of stars simultaneously. Some of those stars are massive and some of them are not so massive. The most massive ones produce a lot of blue light. Examples of that are Rigel in our sky, in Orion is a blue supergiant, whereas older stars tend to be less massive, or less massive stars tend to be redder. Now, the more massive ones that are bluer die very quickly and they go away. So you're only left with the less massive ones, the smaller ones that tend to be redder. So essentially, when you look at a stellar population or even a galaxy, you can tell how old that stellar population is by how blue it is. If you see a reddish galaxy, it means it hasn't had star formation for quite a while. Whereas if you see a blue galaxy, like the Milky Way, the blue pockets are where there are massive stars, and massive stars intrinsically don't live for very long. So you know that there's been recent formation of those stars there. When those two galaxies slam into each other, it causes a burst of star formation initially, but over time, it drives out all of the gas, which is the fuel for new stars to form, and you aren't left with any fuel to form stars. And so you slowly burn off, and the young massive stars die away, and you're only left with smaller stars that tend to be redder, less massive stars that tend to be redder. That was a really convoluted way of explaining that. But the main question that this person wanted was, what does it look like from the Earth? And we have pictures of that. So from the Earth, this is like a time lapse of what you would see in the sky. So this is what, when you look up, if you're in a really dark sky site like Death Valley or the middle of the Utah desert or something like that, and you look up in the sky, here's the Milky Way, the band of the Milky Way, our galaxy that we exist in, and then you can see the Andromeda galaxy is this little guy here, whom many of you may have seen this galaxy. It's beautiful. Now, shortly thereafter, as the Andromeda galaxy is on its crash course with us, it appears larger in the sky because it's getting closer, and it's getting closer, and then we undergo that initial interaction where things are kind of going haywire. There's a burst of star formation. That's essentially what's happening through this. And then actually this image down here in the lower left corner is what things would look like from the surface of the Earth at about 5 billion years in the future. So we haven't fully coalesced into Milkomeda, but we're getting there. And you can see there are still pockets of this red and blue and kind of purplish star formation that's going on. But more of the distribution of the stars are defined by this less featureful Milkomeda structure that tends to be less blue than we saw in our original Milky Way or our original Andromeda. And eventually it'll be kind of a reddish population of older, less massive stars that are left without as clearly a defined disk as we have in the initial Milky Way. So hopefully that made some sense to the person who asked it. Let's see.
And because you showed a galaxy simulation, I'm obliged to point out my husband proposed to me with a galaxy simulation.
Oh, yes, that's right.
Yeah. Just in case you're wondering about my nerd credentials. I still married him, even though that's how he proposed.
That's
Oh, wow.
That's awesome. So Jesse's husband is Dr. Phil Hopkins, who is also an astronomer in the department, but he wasn't able to join us tonight. But perhaps in a future outreach event, we'll
one of us has to be kid wrangling at any given point. So we're like Clark Kent and Superman. You're only going to get one of us at a time. You can have Phil next time.
Okay. I'm going to throw another exoplanet question at both Jason and Jesse here. And that is question 7 by Katie Morinesco. My 8-year-old daughter, Penelope, asks, have we found any evidence of water or ice on any exoplanets or exomoon?
So do you want me to take it, Jason?
Go for it.
Yes. Okay. So to Katie and your daughter, the answer is yes. We have found water on other planets. And that is, a super exciting thing that we're looking for, because the only thing we know all life on Earth needs is water. So we're on this massive hunt for water on planets in the galaxy. So far, we have found water on gas giant planets like the Jupiters and Saturns of our solar system, where they exist around other stars. And last year, we found water on a Neptune-sized planet, a heated up Neptune-sized planet called K2-18. And that was really exciting. And part of the reason that was exciting was it's difficult to look at smaller and smaller planets. And we try to find the best examples we can of a given size to look at. And K2-18 was the best example we had of a Neptune-sized thing, and it had water in it. So that was wild, because we'd seen water around the big planets. Now we were seeing water about the medium-sized planets. So that the reason we're excited is because that means the smallest planets, which are the planets like Earth, the rocky planets, if there's water everywhere in the galaxy around all of these planets, that means the prospects for there being water on the rocky planets as well is quite high. So we have found water, and we're super excited about eventually finding water on a rocky planet like the Earth. But that part we haven't done yet.
Okay, cool. Thank you, Jesse. A follow-up question from Katie. She also asks, have we found any exoplanets with 2 or more moons?
Good question. I'll take this one. We have not yet. We think we might have the first planet with 1 moon, and that's I don't remember the telephone number. Kepler 16 something.
1625.
1625. 1625b. We think that's a gas giant planet, and we think it might have a massive Neptune-sized moon. The data is not 100% definitive. It's definitely something that would be very surprising. It's something that none of us predicted would we didn't expect to see this kind of thing, but the data indicates there might be such a thing. So such extraordinary claim does require extraordinary evidence, and we're not quite there yet, but that's our first prospects of a moon orbiting a planet orbiting another star, so an exomoon. But we're still not there yet. We're still working on it, and maybe in the future we'll find some exomoons.
Awesome. Okay, thanks. A question from our chat that I think there are a few opinions about. Neutron star mergers have been mentioned as the source of the heaviest R process elements found in the universe. Alternatively, collapsars are another candidate. Do any of you have an opinion on this?
Yes, I have opinions on this. Okay. So a lot of my opinion is formed by observations. So there are various theoretical groups that have claimed to predict the amount of elements coming from each of these 2 scenarios. But the problem is that the observations so far, we only have direct observations of only one of these things happening. So we have directly observed a neutron star merger thanks to LIGO, and we found, we were able to follow it up with electromagnetic telescopes, and we were able to see that actual observational evidence that neutron star mergers produce R process elements. And this is the only observed site of R process production. We don't know if it's the dominant site, and so it's possible that other objects such as collapsars, which are extremely massive, very quickly rotating stars that collapse almost directly into a black hole. And some people do think that those could produce some R process elements, but so far we have not seen any observational signatures of this. And people have looked by looking at very old stars that should only be polluted. If collapsars do produce R process elements, then the collapsars should mostly contaminate these stars, the very, very old ones that are not contaminated by anything else. But we don't see signs of R process elements there. And so this suggests to us that at least so far, we don't have any direct evidence for collapsars being a dominant source. That's my opinion.
Awesome. Okay, great. Thank you, Mia. Are there any other opinions about collapsars and neutron stars and our process elements? It's okay if there aren't. Just trying to be all encompassing here. Okay. How about, does strange matter actually exist in the center of neutron stars? Question by 10-year-old Rowan. Thank you, 10-year-old. That's quite an insightful question.
Yes, indeed. Okay, I can take that since that's a little bit what I work on. Maybe I'm gonna share a slide since I have it ready. Let's see if I can do that. Share screen. Do you see that? Okay, so neutron stars, let's go to the previous slide. So neutron stars, for those who are not completely familiar with those, so they are the last stage of quite massive stars. So our sun is not going to become a neutron star, and something more than 30 times more massive than our star, than the sun, will not become a neutron star, but everything in between will probably become a neutron stars at the end of their life. And what happens is that when a star runs out of fuel in their core, the fuel that keeps it up, so it's burning elements in every star to keep being a star, burn elements in their core, so hydrogen into helium, helium into carbon, and so on. When they reach iron, which is the most stable element in the universe, they cannot burn it anymore because they cannot get energy out of it. And so they go supernova, and that's how the neutron star is formed. It's that iron core in the center of the star that remains after all the rest of the star is being expelled with this beautiful event. It's called a supernova. So, and being born in such an incredible and beautiful event, neutron stars are extreme objects. So here you can see the real size of a neutron star. You have Manhattan here, and this neutron star is just about the size of a city. It's about 10 kilometers in radius, so very tiny. But inside, it has the entire mass that the sun has. So like it's a huge mass. So if you take 1 centimeter cube, like this like sugar cube of a neutron star matter, you can squeeze the entire human population in it. So it's very, very, very dense. Here you can see in the Mount Everest, you could fit it into a cup of coffee of neutron star matter. So the question that the 10 years old, very smart guy asked is like, is there strange matter in the core of a neutron star? Is a question that people have been asking a lot, because at such extremely high density, especially in the core, in the center of the neutron star, matter is not like the matter we see in our everyday life. It's just incredibly more dense. If you think about it, the atoms that make your body, for example, right? The nucleus of the atom is like a soccer ball, and the entire atom is the soccer field, right? So the actual matter that is inside one atom, the nucleus, is very, very tiny, right? So most of the space is empty. While in the neutron stars, all the soccer balls are clamped together. All the nuclei touch each other. It's so dense compared to the matter that make us that all the nuclei are together and they actually fuse and merge. And in the center, the density is much higher than the density of a nucleus, of a normal nucleus. It's maybe 10 times higher. So we actually don't know. So in the LHC, the one I was talking about before, like in these large hadron colliders, we try to recreate this kind of like densities, but at much, much, much higher temperatures and energies. And when you do that, even the smallest parts of atoms, like protons and neutrons, dissolves into quark matter. That's what we call strange matter. It's like the components of protons and neutrons. And so people think if we can press protons and neutrons to very, very high density, maybe we can release these particles that make up protons and neutrons that we see in the LHC. We can see, like when we reach very, very high densities and high energy and high temperature in the LHC, we see them coming out. And that's what strange matter is. But in neutron stars, the temperatures are not that high. So, but it's a big question. We just don't know. We don't know what neutron stars are made of. And I think that's what really drives all of us that study neutron stars. These objects are so extreme. There's like a lab, an incredible lab that you could never build on planet Earth, but they exist and they're out there. And if we can study them, we can discover properties of matter that we could never be able to do here on Earth. So the answer is we don't know. It's possible. We need better telescopes to understand it.
Okay, great answer. Thanks, Eladia. Can you
Yes, sure.
share?
I don't know how to do that. Stop share. Okay.
Okay, great. All right. There is another question that we got from Twitter beforehand. I can't get my head around this. How can we see a galaxy that is 13-ish billion years old and yet it's 30-ish billion light years away? So this is a common question that whenever we start to deal with cosmology and the size and scale of the universe, lots of counterintuitions pop up. So I'll try and address this. So when the universe was younger, everyone I think is familiar with the idea of the Big Bang. If not that, then at least the television program, which took place at Caltech amongst astronomers like ourselves, although we were not cast in the film or the television show. Anyway, so early in the universe, when the universe was much more dense and more compressed and was expanding outward, if you had this region of space over here, which will eventually be us, and this region of space, which will eventually form a galaxy that's a long ways away from us, this distance might be, we'll say something like 5 billion light years away from each other. And light was emitted by a galaxy over here. That light has to get over to us before we perceive it. And in the meantime, the universe itself is expanding outward. The space itself is actually expanding. So the light starts moving towards us, but the space in between us is actually expanding. So it's traveling at the speed of light. So every year it's traveling 1 light year, but because the space is expanding, it actually takes 13 billion light years for it to get to us. And in that time scale, this galaxy has continued to expand outward. And actually it now may be something like, as the question asked, 30 billion light years away from us, even though the light has taken 13 billion light years to travel from its previous position to us in that time. So I know that's a little bit confusing. It confuses me sometimes too, but that's generally the principle, and it's all because the universe itself is expanding. And so you get the misperception of things being at the distance that you'd think they would be, when in fact they're somewhere else because they've moved in the time since that light has traveled that distance. Okay, next question. It's a good one in here. What can we learn from exoplanet observations that may apply to our own planet, particularly modeling climate change? Do Jesse or Jason potentially want to talk about this?
I can say a couple of sentences.
Okay.
I think regarding climate change, it's a bit harder. We're not quite yet at the stage where we can understand so much about exoplanet atmospheres that it's really feeding back into our Earth's climate modeling. The data that we can get on Earth, because we literally live on it, is so much more exquisite that I'm not sure we're learning that much right now about climate change with respect to for exoplanet modeling, but exoplanet observations do help put us in context, try to tell us, how common is Earth, how common is the solar system, are other planets like us out there? And these kind of questions are really important, I think. And those are the kind of questions that we can answer right now, or we are trying to answer right now with exoplanet observations.
And I would just add to Jason's comment that we don't need to go to exoplanets to find examples of what happens with climate change. Our very nearest solar system neighbor, Venus, is an example of what happens when there's a runaway greenhouse effect. And Venus is not somewhere you want to spend a lot of time. We did send a lander to Venus a while back, a few decades ago, and they're studying a few more. And that lander, so, we send rovers to Mars and they like roll around the surface and take selfies and have a great time. The lander that went to Venus did not have a good time. It basically took a few photos while it was getting crushed under the heat and pressure and then died. So Venus is our example of climate change and why we should take it seriously.
Excellent, excellent. Okay. Other questions? How about have you ever found an exoplanet with rings?
Ooh, that is a good question. We have a candidate system that is what we see. One of the ways we look for planets, not the one Jason talked about, the transit method, is where a planet goes in front of a star and blocks some of the light. So you're measuring the brightness of the star over and over again, and you see a little dip when the planet goes in front. Now, we did see one star where we observed it over and over again, and instead of seeing one little clean dip that would be like a circular planet going in front of a circular star, what we saw was this amazing series of dips of varying sizes and widths. And one interpretation of that I think is very exciting is that this is a system with a huge ring system, much bigger than Saturn's ring system even. So, echoing something that Jason said earlier about extraordinary claims requiring extraordinary evidence, that is not something we would have predicted or seen. And it's probably something that's fairly short-lived. But if it's true, it's wild. Like, it's just so much, it's like 10 times bigger than the rings around Saturn. So there is one candidate of a system that has rings, and we're looking for more.
Okay. Great. Thank you very much, Jesse. Here's a question from the chat. Why not use an event horizon-like setup or arrangement to observe exoplanets?
Great question. I think this is actually what I was hinting about trying to resolve the surfaces of other planets. So the Event Horizon Telescope is actually a Earth-sized interferometer. It uses telescopes placed all around the Earth and combines all that light together. And it uses, even though there's only like 4 or 5 small telescopes placed all around the Earth, by synthesizing all of their beams, we can actually use an effective aperture that's almost comparable to the size of the Earth. And with that, we can get much higher resolution. We can think about trying to do the same things for exoplanets. However, they have to be at different wavelengths. So the Event Horizon Telescope is done in what's called the millimeter. So these are very long wavelengths. It's somewhere between infrared and radio waves. So these waves, because they're much longer waves, their frequency is much slower. And because of that, we can actually, we can deal with these waves much more easily than we can deal with optical light. Optical light waves, the frequency is very, very short, It's very fast, and it's hard to try to combine light taken from different telescopes put together. We've been able to do it. We've been able to use interferometry. Just last year showed that we could do interferometry of exoplanets, combining light from multiple telescopes in this way, similar to the Event Horizon Telescope for telescopes with baselines up to 100 meters. So that's 10 times larger than any single dish telescope on Earth. But we haven't gotten to the point where we can go beyond that yet. It's hard. The technology is not quite there yet, and we're still working on it. But it's definitely something we're thinking about and something we want to do more of.
Great. Thank you, Jason. Here is a good question. Why not prioritize the observation, the looking for, and the study of exoplanets around the closest red stars and brown dwarfs, and the ones nearest to us and to our star and its planets?
Right. So we do that. There are a number of projects around the world, teams who are studying and looking for exoplanets who are specifically targeting the nearby red dwarfs. Now, one of the reasons why you might do this is because, so when I mentioned the transit method before, which is the planet going in front of the star, if your star is much smaller, then the same size planet blocks a lot more light, relatively speaking. So it's easier to find things like rocky planets around M dwarfs. And, one of the things we're excited about is looking for planets like the Earth. So rocky planets that are in the habitable zone, so they could have liquid water on their surface. So we've actually found a number of those around M dwarfs. So earlier, way back when I mentioned that we haven't found any Earth-like planets around sun-like stars, that statement's still true. But we have found rocky planets in the habitable zone of M dwarfs. And that's why people are concentrating on them. There are a few problems with M dwarfs, though. One of them is that they're so small and faint that they're hard to see. They're hard to detect. They're faint. They don't put out a lot of light. So when you're trying to make these very precise observations, it's frustrating because you're trying to collect as much light from these stars as possible, and they're just like little dull things, just like bloop. So that's one thing that's frustrating. Another thing that's frustrating is they put out their radiation in a different part of the spectrum than our sun. So our sun kind of peaks in the yellow. That's why it looks yellow to us. But M dwarfs actually put out a lot of their energy in UV radiation and X-ray radiation, high energy radiation. And we know that UV radiation is bad for life on Earth. So we find all these rocks that are the right temperature for liquid water, but they've got these high energy particles and radiation coming at them all the time. So it's a little unclear, are they actually good places for life, or are they really terribly nasty places for life? So there are groups that are concentrating on them, but we're not making it our sole focus because of those reasons. There's lots of other real estate we want to look at. But we're not ignoring them.
Okay, awesome. Thanks, Jesse. How about, we'll keep on the exoplanet kick here. Do we observe exoplanets in other galaxies?
Oh, I can do this one.
Okay.
So two answers to this question. Other galaxies are typically way too far away for us to do this. And in fact, the planets that we found so far occupy a very small fraction of our own galaxy, of the Milky Way galaxy. But there's two things. One is that one of our very nearby dwarf galaxies, one of the Magellanic Clouds, there's a candidate microlensing event. So microlensing is a third way to find planets that we haven't talked about yet. It's magic that uses gravity. That's all you need to know. But there was a candidate event that was observed in one of the Magellanic Clouds, which was potentially a microlensing planet. Unfortunately, one of the problems with microlensing is they're kind of one-off events that never happen again. So it's kind of not well constrained, but it's a potential planet in a very nearby galaxy. The other kind of cool way to think about it, so when Mia was talking earlier about galactic archaeology, one of the things we do is look at the properties of the stars in our galaxy and try to reverse engineer where they came from. And what you can see is that our Milky Way has been eating other galaxies for its entire existence. Every time a little galaxy comes along, the Milky Way is just like, chomp. So like the Magellanic Clouds and eventually Andromeda, they're all just kind of eating each other. And those little galaxies that get eaten get stripped into these streams of stars that all share very similar properties because they were all born in this other galaxy. And so we did find a planet that is orbiting a star. So the star is now in our galaxy, but we can tell at some point it was in a different galaxy, a dwarf galaxy that the Milky Way ate and shredded apart. So it was originally an extragalactic planet, but now we've just assimilated it. We're like the Borg. Resistance is futile. You're one of us now. So those are the two ways we have of thinking about extragalactic planets: very nearby galaxies or galaxies that we already ate.
Sorry, I started trying to respond to a question on the YouTube channel at the same
No worries.
time.
I feel like I keep catching you off guard by just like ending, and then you're like, ah.
Yeah, no, that's great. You guys are doing a great job. I like this question. How do you decide, out of all the existing possibilities, which system to study in further detail? I presume this is relevant to the exoplanets because there are so many exoplanets, but I guess this could also be a general question as to, you know, we see all these different systems in the universe, galactic systems, stellar systems. Why do we select a handful of those to study in detail instead of, you know, all of them?
Yes, that's the
I can say a
hardest part.
I can say a couple words about the exoplanets, and then maybe we'll talk about other things. So for direct imaging, we get to select all of them in great detail. It's because there's only been a handful of them, so we can kind of study them all. But I guess we do have to be careful about. We have to think about which ones we're going to study at specific wavelengths and specific observing modes. Usually we try to pick observations that are either keystone systems that are unique or tell us something that no other system can, such as I was mentioning this PDS-70 system. It's the only system where we have planets still in the process of forming. So we really want to study that system in detail because that's telling us something about planet formation, which otherwise we have almost no direct observational evidence for. Other times we try to select a sample. So we want to just like how we do any other science, we're going to construct some sample that's some sort of representative sample of something we want to study. Say, like we want to study, what's the frequency of planets around nearby stars, and we select those targets and select a random sample to study these. Study that how common are planets around nearby stars. We can't look at all of them, so we study a random sample of them and try to infer from there how common are these planets.
Thanks, Jason.
I will add that the problem in astronomy is everybody thinks their object is the most important object and all the resources should be spent on that object. And that's why one of the things a scientist does a lot is write proposals to get money and to get telescope time. And those proposals are you trying to convince your peers that your object is the most important and why that the money and resources should be spent on it. That's like half our job.
That is true.
And also going a little bit away from exoplanets in general in astronomy, you usually select things because you have a question in mind, right? You want to answer a specific question and you think that those particular objects have the answer to that question. It could be, again, a population study if you're interested in like kind of statistic things, or you might want to look for the particular object that is very rare, but it holds the key to some physical answer. So like it's different. You must have a strategy in your head. So you must have a question, and that's how you select your object, because the stars and astronomical objects out there are so many. You always have to select, and you always have to pick the ones that you want to look at, and you have to have a strategy in your head.
That's true. Thank you, Ilari. I like this question because it involves everyone. What, in your opinion, is the most underrated object in the galaxy? It's also pretty broad.
I have one.
Okay.
Micron-sized dust particles. They are everywhere. They contaminate a lot of people's data. They form a lot of the things, like you and me and the planets that we live on. They, they're small, but they are important for almost everything or affect anyone's observations of anything. So I think those are things that people normally dismiss, but they carry a lot of weight just by collectively how many of them they are.
I like that. That's good. Other opinions?
Proper machine readable tables. As an archivist, I would say that everybody ignores the fact that they should be proper machine readable tables.
Anyone else?
I guess I'll add, since you talked about it earlier when showing people what is in the night sky right now, the Orion Nebula, I think, is criminally underrated. It is the closest star forming region to us. And so if we want to study how stars form in a very detailed way, it's the best possible candidate to do that. And I think a lot of astronomers, myself included, tend to overlook it in favor of things that are farther away, because there's a lot more of those and things outside of our galaxy. But the Orion Nebula is pretty cool, and you can see it with your eyes. You don't even need a telescope, so it's pretty awesome.
Criminally underrated. I like that. Okay. Anybody else?
Maybe brown dwarfs. You know, brown dwarfs are like this kind of the bridge between stars and planets. You know, I guess they're very hard to study because they're very faint. But like brown dwarfs are stars, like they're not stars, like they are born like stars, but they don't have enough mass to keep on the hydrogen burning that makes a star. So they cannot burn hydrogen in their core for long enough or at all. And so they fail and become these objects that just keep cooling. But, you know, I think they're very interesting because there's lots of them out there and we're finding more and more of them. And they're really this bridge between how are stars forming and how are planets forming. And I think there's going to be a lot more studies about brown dwarfs when JWST comes up, because they emit very much in the infrared because they're very cold. But I think for now, they're a little bit underrated.
Okay.
I'd say, on my point of view, maybe like solar system bodies, because a lot of stuff is going on in our solar system, and like there's a lot of study to study like on asteroids and stuff. Maybe I'm biased because I'm not really into this field, so I can't feel what's going on there. But like when we study exoplanets, we always see a similarity to what, you know, with Earth, and the same could happen like in the solar system. Probably we could see a lot of stuff going on even closer to us without looking much farther away. I don't know. It's a tough question, actually.
It is. It is a tough question.
Right, piggybacking off Paolo's answer, Pluto.
Pluto. I mean, I didn't want this to get political, but yes, Pluto.
Indeed.
Clearly.
I would probably
Thanks.
say, I'd probably say dark matter, because it never gets any credit because we can't see it or detect it through any other means other than gravitational means, which is a super indirect way of figuring out that it's present. I mean, it plays a big role in the evolution of systems, not on the scales of solar systems, but on the scales of the galaxy or stellar systems. So it does play a role there, but yeah, I think.
It was a question, what is dark matter?
I didn't, we only have 5 minutes. I didn't want to get into that question. I figured we'd save that for next time.
Okay.
I wanted to end on a high note that was related to the talk, and that is, why do you think it's important to study exoplanets?
Ooh, well, we kind of touched on this before with the, putting Earth in context, right? Like, it's an age-old, millennia-old question. Like, are we alone? Is this it? Is this a little rock drifting through space with these like little creatures crawling all over it? Is this it? And so one of the reasons we go and look for planets around other stars is to answer that. Like, are there Earths out there? Are there other Earths? And, you know, one day in the future, will we be able to go there and meet whatever's there? You know, imagine if this was it. Imagine if we were alone forever. I need to know the answer. I need to look for exoplanets so that I know the answer to that.
And I think that the other big question that we want to know is, how did we get here? And one of the parts we want to know from that is, you know, how do planets form, and how did our Earth form? And, you know, we have some geological evidence we can look at, but we can't, you know, time travel as far as we know backwards in time 4 billion years to when the Earth formed. We have to look at other exoplanet systems in the process of formation to kind of to understand and extrapolate from there about how Earth formed.
Excellent. Thanks, everybody. Well, I know there were still questions in our chat. We will write down some of the highlights and try and address those in our next session. We're planning to have, I think this was generally successful aside from some technical problems. Thank you very much, panelists, for your contributions and your insight on various fields within astronomy and astrophysics. But yeah, we'll have another event. Right now we're scheduled to do it next Friday. That may be too soon. We may end up doing it in 2 weeks, but our next speaker will be Yugong Chen, who's a PhD candidate in the department, who studies observational studies using the Keck telescopes to look at the low density gas around galaxies and how it percolates down and fuels star formation and the effects it has on galaxy evolution on long time scales. But yeah, if you have other ideas on ways we can improve this, I'd like to have an observing component, but I haven't figured out a way to rig up a telescope from my house with the computer and the live stream. So yeah, we'll figure something out and we'll post it on social media. Thank you all for attending this virtually, and please stay safe out there, social distance, and hopefully we'll beat down the spread of this virus globally. Thanks, everybody.
Bye, everyone.
Bye.
Bye. Thank you.